Welcome back to Introduction to Electrical and Computer Engineering. I want to cover a couple of little topics that might be of interest to you. And so, hey, we are ANGR 1202. Hey, happy tax day for corporations. All right, so imagine this. Imagine I have a battery, and let's say I have this AAA battery. Now, a AAA battery is going to have a certain amount of energy stored inside of it. And this energy stored inside of it is going to have a characteristic. It's not like, if we were to look at this energy, or I should say voltage. And I don't know, current draw, or I should say load. So if this is a one, oh, by the way, a single AAA battery is how many volts? All right, it is 1.5 volts if it is fully charged and alkaline. Did I spell that right? Because, oh, that looks a lot better. Because the rechargeable batteries typically are a lower amount of voltage. So if it's a rechargeable, and I can't remember if it's 1.3 or 1.2, I think it's 1.3. And this would be like a nickel metal hydride, or some other type of technology. So let's assume that we have an alkaline battery. That would be lead acid equivalent. So at 1.5 volts, you would have its capacity run, and then it would kind of drop off pretty quickly as you were depleting the battery. But notice that it's not a straight down characteristic of the voltage. So as you use a battery, it's going to provide you, and sometimes that chart is, it's a slope that goes down. Sometimes it's mostly far apart or close apart. But it's going to have a certain amount of capacity of what it's able to provide for your system. So one typical capacity would be, I'm going to have a 1.220 amp hour. So that means if I draw an amp of current from this battery, it will last 1.22 hours. Now this battery capacity makes a difference because think about your mobile phones, right? Your mobile phones are running at 3.6 volts. I should say the batteries are 3.6 volts, and it's a single bag which is inside of a plastic case, but it's a single bag of goo chemicals, lithium polymer or something like that. And oh, by the way, have you ever broken open one of those batteries? And what happened? It did what?
It seemed to like crack. I didn't explore it.
Oh, you didn't like throw it in a fire or something like that? Okay, because typically these batteries, lithium, I believe, when it hits air, is kind of flammable. And so if we were to go online and look at YouTube videos on lithium polymer and lithium ion batteries burning, it's kind of like really bright white phosphorus light, which is not fun after, after a couple of seconds, all right? All right, so that's what we have for capacity. Now, think about this. Let's say I want to do a circuit, and I'm not sure if you've actually done these circuits yet. Have you done circuit drawings like that? You know what that is? That's a battery? Okay. But if I have two of them, what I'll want to do, and I'm trying to remember, I think the big side is the plus, right? So that means that I'm going to have current flowing through that is my LED, that is my resistor. Let's say my resistor is going to be 1,000 ohms. And this is how I'm going to light my LED. These are two AAA batteries. So I want you to think about this. Oh, by the way, what's the voltage drop from here to here? All right, it's 3 volts, right? Because we're putting these two batteries in series, not parallel. So here's another question. So, the voltage is 3 volts. What is the storage capacity of these two batteries? When you put them together? Oh, you said still be 1.22. Why is that? Oh, so what you're doing is, even though you have two batteries, right, you could either double the voltage or double the storage capacity. If I put those batteries side by side to make them parallel, my voltage drop would be what across that? 1.5. And then what would be my storage capacity? It would be 2.44 milliamp hours. And so you have to keep in mind that, think of all those electronics that you have in your, that you throw batteries into. What typically are they doing? Are they putting those batteries side by side, or are they putting those batteries in a big long line? Typically a long line, because you're running at 6 volts or 4.5 volts or 3 volts. Or if you have a single battery, of course, that's only 1.5. And only a few electronics will support that. So now, hey, remember our past knowledge that we had? Our past knowledge of current? So I'm going to say with a ideal battery depletion model. In other words, we're going to assume that you will provide 1.5 volts of energy, and then you go down to 0 when you use it all up. How long will this LED stay lit? Now, before we break, here's the quiz, or here's the question, is what thing have we seen in the past you need to worry about? All right, the resistor. What else? The current. What else? The voltage. And what formula have we seen that you worry about all those wonderful things? So, your assignment while we take a break is to turn to your neighbor and figure out, how long will this stay lit? We'll be back. All right, we're online. And by the way, I was being reminded by people that some notes that I'd posted online were wrong. I take no responsibility for something I might have done at 8 o'clock in the morning. So V is equal to 3.0 volts, right? And our resistance is going to be equal to 1,000 ohm. So using V equals IR, we're going to have I is equal to V over R, which is 3.0 over 1,000, which is 0.003. Is that correct? So what we have is our time that we're going to run, which is going to be equal to capacity divided by the load, which is going to be, as we said, 1.22 it's amp hours, not milliamp hours. And this is all over 0.003 amps. So obviously these units cancel out. And the answer is, I believe we had very many people saying 406.6 hours. So that is 16.94 days. Wow! That is pretty cool, huh? Now, what will this be useful for? Maybe to set your expectations of electronics projects that you're going to be doing in the future, right? The fact that we're drawing only 3 milliamps on a circuit is actually really good for very small circuits, small devices. But if you get anything like wireless, anything using any technology like that, yeah, it's probably going to draw a lot more. Question?
Does it matter the resistors after the LED?
Good question. So technically, the formula is the same, right? And some designers put it before, some put it after. So the question is, which one is better?
The question is, because it's after, does that mean it doesn't actually do anything?
Well, no, it will draw the same amount, whether it's before or after.
Does it have a purpose? Would it be better to just put the battery connected straight to the LED?
Good thing. All right. So let's say an LED has in it a very, 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 very small resistance, very small, like 1 million. So what does it mean our current is going to be? Actually, is it the other way around? Yeah, it's small. It's the other way around. It would be like 1 milliamp. Or 1 amp. Or I'm sorry, 1 ohm. So if you have 1 ohm, what does that mean the current is? 3 amps going through that LED. Now, here's the one thing. What destroys electronic circuits? Heat. What generates heat? Resistance. So if you have a resistance value of 1, which is pretty darn close to a straight wire, right? You're going to have a lot of current running very, very fast, which will heat up the silicon in the LED, which will basically melt it. And you will, as we call, release the magic smoke. Because in electronic circuits, it's the smoke that they put inside that makes it work. And when you release the magic smoke, then it doesn't work anymore.
So when you actually build the circuit, you should put the resistor before the LED, otherwise that will happen.
Well, it doesn't matter which one, because don't forget the resistor will clamp or will limit the current no matter where you put it in the circuit. So you're just worrying about the voltage drop. All right. Now, getting back onto the magic smoke, that's a running electrical engineering joke. What does the smoke represent in a circuit if it comes out of your chip? You just melted the silicon and most likely the plastic around it at the same time, which makes a nasty, burning, smoky smell. So the smoke isn't magic, it's just a joke. All right, question over here.
If you put the resistor before the LED, wouldn't it make a voltage drop before it?
Correct, but it's the current that lights the LED. And hey, here's a good question for you. Can you test that out?
Yes.
And how can you test that out? Well, think about this. For lab number 3, you're doing an exercise where you have an LED and a resistor. Switch them up. See if it changes the light on which side you put it on. Oh, which brings up another question where people were saying, which way do you set it up or hook it up? So did I not cover the cathode and anode of an LED? So if you look at an LED, it typically has, oh, that's a horrible picture, all right. Typically has a flatter side, and more importantly, it has the legs are 2 different lengths, all right. So the longer side you put towards the plus, and the shorter one you put towards the minus, and that's the anode and cathode. So an LED is a light-emitting diode. A diode only allows current to flow in one direction. So if you hook it up backwards, you will not ruin it. If you hook it up correctly, but you give it way too much current, you could ruin it. Or for that matter, way too much voltage too. I think these are rated for up to 2 or 3 volts. I can't remember exactly how much. Or 3 or 5 volts. All right, any other questions? All right, we're going to switch now to software. So from that part of the talk, we're going to cover the handouts that I provided to you. And these handouts are the actual code for lab number 4. So now that you understand LEDs and all of the other concepts that we've covered, by the way, anybody not have one of these, you need to grab one of these. There are certain parts of this code that I want to cover, and certain representations of all of this which are important. And so with that in mind, let's go through little bits of these. First of all, when you are programming, and all of you have had 2103, or almost all of you have had 2103, right? Which is ECGR 2103, C++ programming. You know what this is at the beginning of our program, right? Right here. And that would be comments. Comments are very, very good. So I want you to keep in mind that comments are good. Comments are your friends. Why is this? Because when you work on software, by the way, for those of you who are electrical engineering who think you'll never write code, you may not write C++ code, but you will write MATLAB or LabVIEW, or LabVIEW is actually graphical, or some other type. In fact, even if you do LabVIEW, you'll need to write comments in there because you'll forget in a week, 2 weeks, a month, what is being covered. And so, by the way, I'm turning off the microphone because you could hear me anyhow, right? I have at the beginning, notice that this is a block of comments that describe what this entire file is going to do. I have the file name, who I am, who it was modified by the way, this will be you when you write this for lab number 4, what the inputs and outputs out and what it does. By the way, one of the tunes is the Also Spracht Zarathustra, which is the, if you've watched the movie 2001 and A Space Odyssey, it's the one that goes, ah, 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 da, da, boom, boom, boom. All right, we've done this before. Now notice that when I do comments, I also have comments all throughout. So I usually have a nice big header block, and we'll see this later. We have this include file. Now, do you remember what this is for? What's the use of this? The what? I can't hear you. Okay, it's a library, but what does this particular library give you? All right, it actually names things like your P1 out. Because in microcontrollers, it actually has an address and a memory address. And I'm not even going to go into this. This is going to be covered later in other courses. But it's a lot easier to use something like P1 out than to use something like hex 40102. Which, do you know what that means? It's a specific memory address. And actually, I might have too many bits in there. This is for 1 meg. So let's say hex 4010. So just keep in mind that, yeah, we like this because it allows you to substitute P1 out for some address, and that's a lot easier to read P1 out than it is this number sequence. Now, there's another bunch of things in here. Pound defined, you remember what that is? Yes? No? Kind of like a variable. It's actually a way for you to substitute later something like, if I see the letters ASH somewhere in my code, what that means is that I'm going to replace the character string, specifically lowercase a, uppercase SH, with the number 233. And that would be everywhere in the code. Now it turns out this is a music playing application. And so it's a lot easier for me to say, I want to play the following note, C, note B 3rd octave, note D, note E flat, note E, note F, note G flat, G sharp, and others as you go along. So for those of you who are music majors, all we're doing is we're identifying different notes with different frequencies of sound. We'll see this later. Now, another part of this is prototyping. You've done prototyping before, right? Yes? No? All right. Remember, prototype functions, you are going to prototype. In other words, you're going to let the software know that later you're going to create functions that might have the name March, or might have the name Mario, or might have the name Freak, and in this case, Freak is going to take an input of an integer. In all cases, all these functions are not returning anything. More on that later. So let's look at more fun things inside of here. Well, here at the beginning of my code, I put another one of these blocks, and these blocks meaning, hey, this next block of information here are going to be my function, main. And actually, this is what you're going to write for lab number 4 is you're going to complete this section. As a part of this, you're going to put some code here. I'll let you figure that one out. You're going to put some more here. You're going to put some more here. And what the heck, I gave you the end of the while loop and the end of the main program. Oh yeah, loop forever. You're going to put some here. But I'm even telling you, look at these wonderful comments here. Read the switches. If the switches read 0, 0, 0, 0, meaning they're all off, play the Empire March by calling the function march. So I'm telling you here, literally, what code you have to run. So this is actually where, you need to put in your read the port code. You're reading the switches, right? And then you call the music functions. And actually, the way I've designed this lab is you're only really changing code up here, and the rest of this file you don't need to change. I'm providing all the wonderful things for you to work on. All right, does that seem easy? Well, let's look at some more detail in this file. I have a couple of functions here that actually will allow you to delay a millisecond and a microsecond. And I'm actually calling a function that's available somewhere else. And as an example of a function, let's look at this one right here. I'm going to go to this one right now. Oh, I like that big sigh. Is this exciting? This is the Empire March. So in the Empire March, we're going to, of course, give the function definition, or the we'll start the function here. Notice I also have information about here. Here's the name of the function. Here's the input. Where's the output? Oh, beep is going to play the Empire March. And look at that. A. Remember A from earlier? A. So this was 440. So based on my pound define, when we go through the compilation of this, it is going to replace that letter A with 440. Now what does that mean? Well, we'll see. Here's a function that's called, right? So there's a function that's called beep. So somewhere beep needs to be referenced, and so let's just kind of jump forward to beep. Or jump back to beep. Where did I put beep?
It's back to beep.
Oh, there we go. So there's beep. So here's the function beep, which my input is unsigned integer duration. So we're inputting the note and the duration of that note. So if you actually look at how things are played, this would be, it turns out to be 500 milliseconds. So you remember what the Empire March sounds like, right? Well, that's A, F, C, sharp, etc., etc. So 500 milliseconds, A plays, 500 milliseconds, A plays, 500 milliseconds, A plays, and then F here. Now, one thing that we've kind of done here is this function beep. We're doing some math. We're actually identifying time with respect to our microcontroller. And here, P1 out, bit 1. So that means you need to hook up your speaker to bit 1 of port 1, and it is actually going to turn it on and off for certain amounts of time. It'll do that for to play that note. And then when the note is played, then we'll delay for 50 milliseconds so that you can get individual notes. Because if I didn't put this delay in there, instead of being it would be so you wouldn't have the individual notes. It would just kind of run together. Remember, we have something up here called void, which means that we're not returning anything from this function. Going back. So remember, this is code that will run. This is your code, and what is it doing? Beep, 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 beep. Oh, and we also put an extra delay in there. Because as you go through, you're going to delay about a half a second. And then, et cetera, et cetera, et cetera. And then, by the way, this tune was actually provided by Texas Instruments. So they're the ones who added these funny comments. Start of the interesting bit. Okay, whatever that is. More interesting stuff. This doesn't quite get it right somehow. This is really fake electronic music. So it's going to be really tough to be able to get something that is really, really clever. If I really wanted to make good sounding music, you could actually play with harmonies and do some other tricks with a single speaker. I think if you think about the old Mario Brothers games, you know, yeah, that's kind of fake. But if you listen to some of the current ones, they sound so much better. But we're just making this easy. Oh, so Mario, here you go. Here's Mario. One of the students that I had in a previous class actually did this. They must have been insane. And then here's the thing, Space Odyssey, etc. So now I have provided you all the skills that you need to run this or work on this lab. Question?
How does volume work?
Volume. The answer is there is no volume. Actually, there is a way you could do this, and that would be if you, instead of using the single resistor, if you put a potentiometer in there, you can give it more energy or less energy. We just scaled it back so it wouldn't be too loud, and everybody doing it at the same time would drive you all nuts. But usually it's a potentiometer, and actually you would have an amplifier and then a potentiometer attached to that, which will allow you to introduce more current as you're playing it. And by changing the frequency, you're changing the way it sounds. By changing the amount of current that it's going to source, you change the volume. So now you have all the skills for you to think about this exercise. And so what I'm going to have you do is now you're going to work on, so that's all I have. Thank you very much.